The WEG CFW500 drive has true field-oriented control. It's also known as vector control because the drive takes the current applied to the motor's stator, which you can think of as a vector, and breaks it up into two orthogonal components, one to directly control the rotor's magnetic field and an orthogonal component to control the stator's magnetic field. Keeping the stator's flux vector oriented 90 degrees relative to the rotor's flux vector is what gives us the maximum torque per amp. So to change the torque, the drive's job is to keep those two vectors oriented at 90 degrees and just change the amplitude of the torque current vector, which is why we call it oriented or vector control. Now that's complicated because this whole thing is rotating at the speed of the motor. The drive can do that because it uses a feedback sensor, usually an encoder mounted on the shaft of the rotor to tell it exactly where the motor's rotor is. All of which means, when using vector control, the drive can accurately control the motor's speed and torque, and it can provide full rated torque all the way down to 0 RPM. That's something you can't do with any other mode. And it turns out that with a little mathematical magic, the drive can also do vector control without a sensor. We call that sensorless vector control. The limitation is it can only do it for roughly the top 90% of the speed range. Below that, and it falls apart. The drive needs that sensor to do the low speeds. Now that's the bad news. The good news is that for the top 90% of the speed range, you get fantastic accuracy and control over your motor for free because it doesn't require any extra hardware. And for the vast majority of applications, sensorless vector control is all you'll ever need. So both are way better than the standard volts-hertz, and sensorless vector is free. Why wouldn't you use them instead of volts-hertz? Well, there's a slight downside. Both vector control and sensorless vector control require that you tune the drive to the motor so the drive knows exactly how to manipulate the currents to maximize the motor's performance. Volts-hertz works right out of the box, so it takes almost no effort on your part to get things running. The good news is the CFW500 drive makes tuning super easy, and it only takes a couple minutes. So you might want to consider taking advantage of one of the vector control modes if you want better control over your motor. Let's do a couple examples so you can see just how easy it is. We'll do vector control with the encoder in this video, and then do sensorless vector in the next video. And there's a third video that gives you some helpful hints and covers the things we skipped in the first two videos. I'm using this single-phase input, 1 horsepower 3-phase output drive, and this inverter duty motor that has a built-in encoder. Now I can't emphasize this enough. When doing vector control, you really need to use an inverter duty motor. Because vector control is constantly manipulating the magnetic fields, it places much more demand on the motor, and especially if you plan to be operating at low RPMs where the motor can get very hot. Inverter duty motors are designed to handle that. General purpose motors aren't, and you'll actually see a much shorter service life, and in some cases, the general purpose motor will even burn up. Now, can you get away with a general purpose motor while you're learning about vector control? Sure. But in actual application, please do yourself a favor and use an inverter duty motor. The initial cost is higher, but the long-term cost will be much lower. Are all inverter duty motors created equal? Nope. But that's a subject for another video. Just know that a better motor will get you better results, and that any of the high-performance inverter duty motors at AutomationDirect.com will get you in the right ballpark. The CFW500 drive comes with a standard I/O module under this cover, which you need to swap out with this encoder module. I wired the motor's encoder to that module like this. This is what the motor's built-in encoder looks like. Notice that we're using the encoder module supply to power the encoder. There's no need for an extra supply. I love that. Now it is limited to 150 milliamps, and that's shared with all the other I/Os on the module. This encoder uses 100 milliamps max, so keep that in mind and make sure your encoder plus any I/Os that you're using don't exceed the 150 milliamps. You'll want to use a good shielded cable with twisted pairs that are individually shielded and an outer shield around all that. Connect all shields at the drive end only. That prevents grounding issues, especially if the motor is remote and possibly at a different potential. And of course, keep the encoder cable as far away from the motor's power cables as you can. Don't run them in the same cable tray, for example. This is the cable I'm using in this demo, simply because that's what I had access to. It doesn't have an outer shield, which for our little demo here in my electrically quiet office is fine. Here we go. Apply power to the drive. This is a list of everything that needs to be done to tune the drive for vector control. It looks kind of intimidating. The good news is, most of this is read-only or default stuff, so I'll gray those out. Now we only have a couple parameters to set. Let's go to parameter 204 and set it to a 5 to reset the drive to 60 Hz factory default, just so you know where I'm starting from. Go to parameter 27 and verify it's a 10. That tells us the encoder module is installed correctly. Parameter 39 shows us the encoder count. Is the encoder counting? Yep. Is it increasing when rotating in a forward direction? Yep. Decreasing in reverse direction? Yep. Looks like we wired the encoder correctly. Now notice that even though this is a 1024 PPR encoder, the count we get is 4096 PPR, which means the drive is using all 4 edges of the encoder cycle to get 4 times the native resolution of the encoder. And we can see it's working correctly in parameter 38, which shows us the rotation speed in RPM. If I rotate this at roughly 1 revolution per second, yep, we get roughly 60 revolutions per minute. Perfect. Now, if you forget to wire the encoder or it isn't wired correctly, you'll get an alarm 79. I love that the drive checks that for me. One last check before we start. Hit run. Is the shaft rotating in the same direction as this little arrow when looking at the motor from the load? This one is, so we're good to go. If not, then power down, swap any 2 of the motor leads, power back up, and check again. It should now be rotating correctly. If changing the motor's direction is not an option, maybe your motor rotates backwards but it's working great in an existing application, for example, then swap the A and the B wire pairs of the encoder and then verify that the pulse count goes up when the arrow shows the rotation to the right. Great! We're ready to start tuning. Drop into the parameters groups. And here's the good news. Scroll to the startup menu and enter that. This is going to walk us through everything we need to do in the order we need to do it to tune the motor. That makes tuning super quick and easy. You don't have to think. Just follow the prompts. It automatically drops us at parameter 317, which we set to a 1 to tell the drive we want to configure it for vector or oriented control. Config is now lit up on the display, and it will stay there till we're done. That sends us to parameter 202. Set it to a 4 to tell the drive we want to use vector mode. Parameter 296 is a read-only parameter that shows us the line voltage. It's just a quick check to make sure you have the drive you think you have. If this doesn't match what you think you should have, then stop now and get the right drive. Service factor is fine, and parameter 400 is where we enter the exact line voltage we're using, and the 220 default is what we're using. Parameter 401 is the rated full load amps. If we look at the motor's faceplate, we see this motor is rated for 3 amps, so we'll enter that here. The frequency is 60 Hz, that's fine, and according to the motor's faceplate, its rated speed is 1725, so I'll enter that here. A 5 for this guy is 1 horsepower, so that's good. We do have a 1024 PPR encoder, so that's good, and this is a self-ventilated motor. And we're done. Now we just drop into parameter 408 and set it to a 3 to do a full tuning with the load connected to the motor shaft. Now beware, this is going to rotate the shaft. I'll go ahead and start that along with a stopwatch so we can see how long it actually takes. The bar graph down here shows us the progress. Now if you're nervous about tuning with the motor driving your system, you can start with mode 1, which doesn't move the shaft, but also does the least tuning. It really just measures the resistance. You could then try mode 2, which does rotate the shaft, but with the motor not coupled to your system. It'll do a better job, but it still won't be optimized for your system. Then, when you do have the load connected, you can run mode 4 to update the mechanical time constant, or just run mode 3 like we're doing here. It only takes a couple of minutes. Now, if you have the tuning constants already from the motor's manufacturer, then use those. These calculations are all based on WEG motors. I hear the motor thumping as the drive hits the motor with current pulses. I'll turn up the audio so you can hear it. They're getting louder and louder as the drive issues larger and larger current pulses. I'll turn that back down so we don't have to listen to it. Eventually, the shaft will spin up a few times and the tuning will be done. I'll fast forward the video so we don't have to wait. Okay, it looks like that took this much time. Not bad. Well, that's it. You're now ready to use this system and can expect to get full rated torque down to 0 RPM. In fact, let's go to parameter 133, the minimum frequency, and set it to 0. Now if we run the motor, we can see we can actually run it down to 0 Hertz. Cool. You can't do that with volts Hertz. I'm going to increase this to 2 Hertz. The bar graph is showing us the percent of rated current that we're using. Watch the bar graph as I grab the pulley. Did you see that? The current increased as the drive tried to do everything it could to keep the shaft spinning. Now the rated torque on this little motor is only 3 foot-pounds, so for this 4-inch pulley, I only needed to be able to hold 9 pounds so I could get away with this. Don't just grab your machine unless you know exactly what it's capable of and you know it's not going to hurt you. Just for fun, let's compare that with the exact same drive, but set up with volts Hertz mode. This is what I did to get there. It's definitely a lot easier to set up. Now if I hit run and adjust the frequency, we see that the motor struggles to run at anything below a couple hertz, and that's being generous. And notice the current. The drive is sending 100% of rated current just in hopes of keeping the shaft spinning. And if we wait long enough, we get a motor overload fault. Volts Hertz does not like to operate at low frequencies. Okay, I'm back in vector control mode. And if I drop to 0.1 Hertz, we see the current is modest, so we aren't going to get a motor overload fault. Now if I stop the motor, there's something odd here. If I reach up and try and spin this pulley, forget it. It doesn't want to spin. And look, the current bar graph tells us it's injecting roughly 40% of rated current into the motor. Well, that explains the resistance I'm feeling. But why is the drive injecting current when the motor's stopped? Well, when you're in vector control mode or even sensorless vector mode, the magnetizing current is always active. But that means the motor's always burning power even when it's not running, which costs you money. If you don't need that, then just go to parameter 181 and set it to a 1 to turn off the magnetization current when the motor stopped. Now it takes effect immediately. If I toggle it a few times, you can see the current on the bar graph come and go even though I haven't hit return yet. If I disable it, spin the pulley, and quickly enable it, you see the motor abruptly stops spinning. I'm going to disable it and exit. And again, when we see no bar graph current, the motor's free to spin. That ought to be enough to get you up and running with field-oriented or vector control. Join us in the next video where we'll do the exact same example but without an encoder. And be sure to watch part 3 where we share some helpful hints and cover the things that we skipped in the first 2 videos. Meanwhile, click here to learn more about the WEG CFW500 variable frequency drives. Click here to learn about Automation Direct's free award-winning support options, and click here to subscribe to our YouTube channel so you'll be notified when we publish more videos like this one.